Welcome, everyone. So in 7.2, we're going to talk about the circle again. We did already talk about it earlier in the semester. So if you're looking for like a detailed version of how to work this formula here, you might want to revisit that video. And then we're also going to add into that, brand new, the ellipse, which is another one of our conic sections. So we've already discussed the parabola. So now we're moving into these two. The circle is also a conic section as well. Okay. So as far as the circle is concerned, we already derived this formula from this picture, and we've already used it to find the center and the radius, or given the center and the radius, write this equation. But what we're going to learn in this section is that a little bit, but also how do I get it into this form? Because quite often the circle isn't given to us in its standard form. Okay. All right, so let's go ahead and take a look at that. All right, so our job is to get this into standard form. So I'm going to write the goal up here, just so we kind of know what we're working towards. Okay, so that's going to be what we work towards. So what we're going to do is we're going to move the x terms closer together. So I'm going to take x squared and negative 4x and move them closer to each other. And I'm actually going to leave a little space after the 4x, because what we want here is a factorable trinomial, and one that factors as a perfect square. And so I'm going to leave some room. Then I'm going to write my y terms. So I'm going to put y squared and negative 20y close by as well. And then any constant, I'm just going to move it over to the other side. So this will end up being a negative 68 because we subtracted it over. And again, I'm leaving some space after that negative 20y because I also want to add a number here to give me a perfect square trinomial. Okay, so it's been a while, but we have a formula for completing the square. So let's just kind of rewrite that down, remind ourselves of it. It comes up quite a bit in math. Okay, and it's written a lot of different ways in every textbook. I write it like this, so in case the b is fractional, but it's also written like this in some textbooks. Okay, I'm just going to erase that so I just don't confuse my students, but in case some other students have seen that other one, they'll know what I'm talking about. Okay, so we got our formula. I'm just going to put it in a cloud, so that's important. Okay. So we're going to complete the square twice within one problem. You can see up here in our formula that we do have two perfect squares. And so that's why we're going to be doing it twice. The first time we'll do it to the negative 4. So we're going to take half of b and square it. So we're going to take half of negative 4 and square it. Well, half of negative 4 is negative 2. And then if we square that, we get 4. So I'm going to add 4, but if I add 4 to one side of the equation, then I have to add 4 to the other as well. Now we're going to complete the square again, but this time we're just going to do it with the negative 20 as our b. Okay, so we've got to do half of b. I'm going to square it. So we're going to do half of negative 20, which gets us negative 10. And negative 10 times negative 10, that's 100. So we're going to put a plus 100 here and a plus 100 over there. Okay, so now we're going to go ahead and factor each one of these trinomials. Now remember, you can do it in the way, oops, screen there. You can do it in the way that we've been factoring all semester. Let me just take one of them. I'm going to erase this in a second, but let's just take one of them. So when we normally factor, we do the x and we say, what are the factors of the last number that add up to the middle number? And so the factors of 4 that add up to negative 4 would be a negative 2 and a negative 2. So that means that I could write this polynomial, instead of writing it as like x minus 2 times another x minus 2, that I can write it as x minus 2 squared. You can still use that. But I do want to point out that every single time, the number that is inside the parentheses before you square that is the number that goes right here. So if you want to shortcut the process, you could just say, okay, I know it's going to be x minus, and then I'll just draw a little arrow from this -2 to right here. And so that way we know that's where we got it. So right before you square, that's the number that's going to work every time. And let's just check it again, on this next one, and then we'll never do it again. We'll use the shortcut. Okay. So for the next one, it's y squared minus 20y plus 100. So we would be looking for the factors of 100 that add up to -20. Well, -10 times -10 is 100, but -10 plus -10 is -20. And what do you notice? There was a -10 inside. So this is great news. This means that we have a really nice, quick way to get this factoring done now. So we're just going to put -10 in the blank. And again, I'm just going to draw a little arrow from this figure. Okay, so then if we add everything up on the right-hand side of the equation, those should add up to 36. So that's going to be one answer because the directions do say to write the circle, equation of the circle in standard form. Okay. But then from that, we want to identify what's our center and what's our radius. So remember that for the center, it's super easy. You just change the signs. Pretty much anything that we're pulling out of the parentheses, we change its signs. So instead of it being a -2 for the x value, it's going to be a +2. And instead of a -10, it'll be a +10. All right, and then when you look at the formula, the right-hand side, the 36, is really r squared. Okay, so that means that in order to find the radius, we're going to let r squared equal 36. And then we're just going to have to square root to get r equals 6. Now, we don't have to put the plus or minus in this case, and that's because a radius is a length, and lengths are never negative. You're not going to get out your measuring tape and measure some radius of a circle and say it was -6 long. You're going to say it's 6 long. So we don't need the plus or minus whenever we're talking about lengths or distances. Okay, it's been a while. Hopefully this last part is still in there. This part up here is new. Okay, let's do another one. All right, so we grouped together the x terms. So I'm going to put x squared and -2x closer and a space after them. Then I'm going to put the y squared plus 6y with a space after it. And we are going to move the constant over to the other side. So we should have a -1 on the right-hand side of the equation. All right, now we're going to go ahead and complete the square. Right, so we're going to take half of the square. So the b for the x's is going to be -2. Well, half of -2 is -1. And -1 times -1 is +1. So we're going to put a +1 and a +1. Now we'll do the same thing, but this time with the b for the y term. Okay, so let's go ahead and take half of 6 this time. So half of 6 is going to get us 3. And 3 times 3 is going to be 9. So we're going to do a +9 to one side of the equation and a +9 to the other. Okay, so now we're going to go ahead and factor these. And we know they're going to be perfect squares, right? And we know where to get the numbers. We're just going to take the -1, plop it in right here. And we're going to take the 3 and put it in right here. How easy is that? All right, and then when we add up the right-hand side, it's kind of nice that the -1 and the +1 cancel each other out. So it looks like we're just left with 9. So there's our equation of our circle. So let's go ahead and get the center. So it looks like the center is going to be 1, -3. And then if r squared is 9, and we square root those, it looks like r is going to be 3. R is going to be 3. All right. hopefully on that second round, you got a little bit better. Okay. All right, let's go ahead and talk about the ellipse. So we're going to look at how to construct an ellipse. Now, maybe when you were in high school or at some point in your life, you had used the compass to construct a circle. So basically, you put the sharp end of the compass at the center and you opened up the compass a certain amount and you put the pencil in here and you just swung it around and you created your circle. Okay. Well, now we're going to look at with a video how to construct an ellipse. It's kind of interesting. So let's read this definition. We'll go look at the video and it's going to help us get the foci formula and just kind of understand the pieces of an ellipse a little bit better. So an ellipse is the set of all points in a plane, the sum of whose distances from two fixed points, the foci, is constant. The center of an ellipse is the midpoint of the segment between the foci. So an ellipse basically looks like what you've probably heard of as an oval. And your foci will always lie inside the ellipse along, kind of like I call these diameters with like quotes around it, air quotes. Because like we know the diameter of a circle goes all the way through. So it's kind of like a longer diameter that's called the major axis, and like a shorter diameter that's called the minor axis. But anyhow, the foci are going to lie along the major axis. So this line that slices all the way through. Okay. So whereas your compass, you would put the sharp end in the center here, these two foci are kind of acting like that sharp end of your compass. So we're going to go watch a video. I love this video that this guy does. It's if you're wanting to know about eccentricity and you're wanting to like discover, how an ellipse changes if we move the foci and stuff, then this is a really, really great video. I probably won't watch the whole thing, but we'll watch enough of it to where we'll get the idea.
Ellipse 4, the pin and string method. I have two drawing pins pressed into the sheet and a string attached to them. To get the pins to grip, I have placed a piece of timber between the sheet of paper and the text square drawing board. The pins are located at the focal points of the ellipse. Start at one end of the major axis with the string taut on the pencil in contact with the paper. Draw the elliptical curve. This is a very smooth way of drawing an ellipse, but not suitable for an examination situation. The string is the length of the major axis. I've moved the pins in now about 10 millimeters. Now the string comes out further, so the ellipse is going to be wider. Same length, but wider. Now that's one half of it, and the top half, and that's another ellipse done. The string is the full length of the major axis. In other words, it goes up there and folds back. But if we took that small piece there and put it in from the pin out to the end, the string would reach from one end of the major axis to the other. So the string is the length of the major axis. Now this is the string. When it's stretched out, it's exactly the length of the major axis. When I bring it up to the top here, this is half of the major axis and this is half of the major axis. Now I'm going to move the pins into the next position. Now the pins have been moved into the next position. This is the third ellipse now, and again, the minor axis is increasing in length as the pins get closer to the center. Now these points here are called the focal points. That's the focal points of the ellipse. There's two focal points on each ellipse. Now I've just used one pin, so I should get a circle now. So the string is attached just to one pin in the center and just draw the curve around. And that's a circle. And that's ellipse.
Okay, so very good video. It's interesting to see that. You can see that as the pins, as the foci, in other words, moved closer and closer to the center, the ellipse became much more circular. We actually have a word that measures how circular an ellipse is, and it's called the eccentricity. The book that we're using doesn't cover the eccentricity, but for those of you who maybe that is in your class, you'll be able to understand your eccentricity formula a little bit better with that video. I'm going to put that video in the link so that you can watch it again on your own and maybe see the rest of it. There wasn't very much left, but so hopefully that can help you. And we're going to revisit it when we derive our foci formula. All right. So we're going to start with ellipses that are centered at the origin. Now, something that I want to mention is we have these words in English that are similar to these words in math, okay? If you say ellipses, that's the ... And that's not what we're doing here. If you're talking about the plural of an ellipse, it's just going to be ellipses. So you might accidentally find yourself saying ellipses because you're used to that word. And we have hyperbolas and there's hyperboles in English, okay? But for here, it's just going to be hyperbolas when we do the plural of a hyperbola. Okay, so let's just kind of go over some of the pieces of an ellipse. Let's see if I have an ellipse on here. Yes, I do. Perfect. Okay. Okay, so I'm going to draw them both ways. They're going to either be, horizontal or vertical. So the line that goes through the longer, like I said, the longer diameter kind of, this is called our major axis. The points at the end of the major axis, these are called vertices. Okay. Individually, they'd be a vertex, right? But the plural would be vertices. And of course, the line or the middle here would be the center. I'm not even gonna write that down, that one's so obvious. But then the shorter diameter, aka, right, like quote, air quotes, that's going to be the minor axis. So we have a major axis and we have a minor axis. And then in the textbook we're working with, it doesn't really have doesn't talk about those points, but some textbooks do. So these can be called many different things. Endpoints of the minor axis is what they were in my last textbook, and co-vertices are what they were in my textbook before that. I kind of like co-vertices because it kind of goes along with the fact that these are called vertices, but these don't quite get as cool of a title, so they're like the co-vertices. But yeah, those are going to be your minor axis endpoints, your co-vertices, whatever. Okay, and of course that could flip and change, if the longer segment through the ellipse is this way, well, then that's going to be our major axis now, okay? And then these, of course, would be the vertices now, since they're along the longer of the two. And then if we take the segment, the shorter segment through the ellipse, then that's what we call our minor axis. Minor. And then these could be called our co-vertices or our minor axis endpoints. Okay. So the foci, you can see in these pictures here, are always along the major axis. Those pins in his YouTube video, right? So the longer the major axis is vertical this time, so then the foci are going to lie along that. So if the longer one's horizontal, then they'll be on that line. If it's vertical, they'll be on that line. Okay. So we have some important formulas here. These are really big. We have our foci formula kind of hiding over here, so make sure that you see that. Again, this textbook doesn't really talk about minor axis endpoints. So for my class, this isn't going to be a big deal, right? So if you want to cross that off if you're in my class, then you can. but I know in every other class I've taught, we have talked about the endpoints of the minor axis. So I'm going to leave that up there for people from other classes. Okay, so what's kind of interesting is that the ellipse and circle formulas are very similar, and I'll talk about that more in a second once we get into ones not centered at the origin, but I just wanted to make sure that we do make that kind of clear. Now, before we start on a problem, I do want to make sure that you understand A, B, and C. If you're going to be successful in this section, you have to know what A, B, and C are. Okay, have them memorized. So A is going to be the distance from the center to a vertex. Okay, so that's going to be the letter A. So let's say that the center is here. Okay, then that means that A would be this distance right here. Okay. Then B would be the distance from the center to a minor axis endpoint. So that's going to be B. And then C is going to be the distance from the center to a focus, to one of the foci. That's going to be C. So let me kind of just make sure A is a little bit clearer, you guys. Let me draw something like this so you can understand. A goes all the way. So it's always about from the center. So from the center to a vertex, from the center to a minor axis endpoint, from the center to one of the foci. Okay. And that's if it was, longer in the vertical direction, right? Then that would, of course, look like get both the major axis and the minor axis in here. And that would look like this. Now we would have A from here to here. We would have B in this segment. And if one of the foci were like right here, then C that distance. All right. It's kind of easy for me to remember foci, because it's got a C in it. And that's how I remember that that's the one that's going to be C. And then like the kind of, how we have the major axis and the minor axis? It seems like the major should be A and the minor should be B. So make sure you understand these and you will be very successful because all of our formulas, look at them. All of the formulas involve these A, B's, and C's. So you've really got to have an understanding of each one. Okay, so let's go in and graph our first ellipse. They're actually not that bad to graph. All right, so let's start off by finding A squared. Now, A squared is always going to be the bigger number of the two. So we might want to note that A squared is always the bigger number. This is only for ellipses, though. So that means that A squared is going to be the 25, and that B squared is going to be the 4. It's not going to be A squared's always in this position. It's going to be the bigger number. So like, let's look at the next one, for example. If we go to that one. Oh, it's not written in the top one. Let's go to this China one. Okay, none of them are written. But it will come across them and I'll point it out, okay? All right, so we need to find A and B. So if we square root, we'll find A and B. So A must be 5 and B must be 2. Okay. All right, then the center for this ellipse, if you're looking at the X and the Y's, there's nothing after them. So our center is going to be 0, 0. And what I mean by there's nothing after them is we could easily have X minus 1 squared and Y plus 5 squared, right? And in that case, it would be 1, negative 5 for the center. If you don't see anything following the X and the Y, then you know that you are centered at 0, 0. So I'm going to draw my center. Now I'm noticing that this A squared, the 25, it's underneath X. So I'm going to make a comment here that A is under X and that the B squared is underneath Y. So this one is under Y. The reason why that's important is because If it's underneath x, then I'm going to move that much in the x direction. So I'm going to go 5 to the right, 1, 2, 3, 4, 5. And I'm going to go 5 to the left, 1, 2, 3, 4, 5. And then the 2, that was the b equals 2, which was under y. Then I'm going to go 1, 2 up in the y direction and 1, 2 down in the y direction. And now I have my ellipse. Now your ellipse will be longer in the x direction if the bigger number is under x. So let's say the 25 had been underneath the y, then we would know that our ellipse would be bigger up and down, like vertically instead of, or in the y direction, however you want to say that, instead of horizontally in the x direction. Okay, so we identified the center. Now let's identify the vertices. So the vertices in the picture you can see are at 5, 0 and -5, 0. So in other words, plus or minus 5, 0. Okay. So you're always going to use the A to get the vertices. And since it's bigger in the X direction, that's why we placed it right here where the X was. Okay. All right. And then we're going to go ahead and get the foci. So remember, the foci doesn't involve the letter A. The foci involves the letter C. So we're going to have to hunt down the letter C. So there is our foci formula that was written on that page of formulas. And it's kind of like the Pythagorean theorem. It's a squared minus b squared equals c squared. We'll talk in a little bit about why that is the way it is, okay? All right, so let's go ahead and substitute in a squared. We already know it's 25. B squared was 4. So that gives us 21 equals c squared. So we're going to go ahead and square root. And we get that c equals plus or minus the square root of 21. 21, let's kind of see how big that is. Okay. Guys, I've got so much stuff going on here. Yep. How many slides do I have open? Okay, finally. Whew. Okay. Square root of 21. And then it's like 4.6-ish. Okay, now we don't need that for like the answers that we're going to put in because we don't want to round. But like as far as like graphing it, I kind of would like to know it's 4.6 because I'm up here and I'm going to go on the major axis. 1, 2, 3, 4.6. It's going to be super close to the edge, right? Really, really close to the vertices in that case. That's where they would lie. All right. So when I put that in over here, I'm not going to use the 4.6. I'm going to put plus or minus root 21, comma 0. Okay. Now we put it in the X spot again because it's in the X direction. If I had gone up and down to it, then I would have put it in the Y spot, but it's always got to be on the major axis. So it's kind of going to match the vertex, right? If you did it to the X for the vertices, then you're going to do it to the X for the foci. Okay, I think we got everything that we needed that this was asking of us. Go ahead and fix that. Now the next one isn't given to us in standard form. We're going to have to get it there. Okay, so remember, our goal is either to have x squared over a squared plus y squared over b squared equals 1, or maybe the a squared is underneath the y instead of underneath the x, making it bigger in the y direction. So this would be one of these. This would be one of those. Okay, so that's our goal. So looking at our goal, you can see that the right-hand side is going to be 1. And that's going to be the case for hyperbolas too, you guys. So if we want to make the right-hand side 1, we have to think, well, how can we do that? We divide by 441, then that is going to make it a 1. So 49 goes into 441 9 times. It's kind of like you're reducing a fraction. Okay, so you could say, okay, it goes in once, it goes in 9 times, and that's why we ended up getting x squared over 9. you have the calculator that we've been using for the class, it reduces fractions for you. Okay, so cool. So 49 over 441. There, 1/9. So you can see the 9 needs to go on the bottom. Okay, so then if we did the same thing over here for the other one, 9 goes in once, 9 goes in 49 times. Yeah. And so it looks like we're going to have a 49 in the denominator. Cool. We got this into the standard form for an ellipse. So we can see that again, the center is going to be 0, 0 because there's nothing following the x and there's nothing following the y. Now this time the bigger number, the a squared, is underneath the y. And the b squared is underneath the x. So when we square root to get our a and our b, we get that a equals 7 and b equals 3. And I'm going to go ahead and remark here. This was under y, and this was under x. So we're going to go 7 in the y direction this time. And then we're going to go 3 in the x direction. Now we are ready to graph our ellipses. They're actually not that bad to graph. They might be better to graph than lines, you guys. You don't have to worry about if your slope is slanting the right way or anything. Okay, so identify the center, yep. Then graph it, we did that. So we just need the foci and the vertices. Well, the vertices should be pretty easy because they're right there staring at us. So you could do it without a graph. We know that a is 7, and we know that it's in the y direction this time. So you could put plus or minus 7 in the y spot. But I always like to go to my picture just to make sure that that's true. Well, 0, 7 is going to be this vertex, and then 0, -7 is going to be that vertex. So that looks good. The major axis is vertical this time, so that's why we're putting it in the y spot. All right, so now we have to go and get our foci. Now we know that they lie along the major axis. You know, they're probably somewhere around here, right? Okay, so let's go get the specifics of it. Okay. All right, so a squared minus b squared equals c squared. So we know a squared is 49 and b squared is 9. So 49 minus 9 gives us 40. So we're going to go ahead and square root. And this radical will actually break down. The last one didn't, okay? But because the square root of 40 is 4 times 10, then this is going to become, don't forget a plus or minus, right? Plus or minus 2 root 10. All right, so our foci lie along the major axis too. So we're going to put that plus or minus 2 root 10 in the y spot again. Now 2 root 10, actually it's easier to put square root of 40 in the calculator. So let me put square root of 40 in there. Equals 6.3-ish. Oh, I keep closing that out and I'm going to need that. Darn it. Okay, 6.3. So if I went 6.3, 1, 2, 3, 4, 5, 6.3, I'd be like right there. 1, 2, 3, 4, 5, 6.3, I'd be like right there. So our foci do manage to lie inside the ellipse, which is always good. We're checking to make sure that's the case. It can never be outside of it, and that they lie along the major axis. All right. So there's a couple centered at 0, 0. Okay. All right, so now here's our formulas, and these are probably the more important ones. If you get like a note card, these would be the ones I would write down because they encompass everything. But these are going to be centered at HK, so in other words, anywhere. And so the only thing that changes on the formula is that there's an x minus h squared and a y minus k squared, instead of it just being an x squared and a y squared. Nothing else changes, okay? So our center would be HK, because we always change the signs when we pull stuff out of the parentheses, right? We change the signs. And then again, if it's bigger in the x direction, then we're going to be, for the foci, doing plus c to the x value and minus c to the x value. And then the vertices is the letter A. We're going to do that to the x value. Okay, if it's bigger in the y direction, then we're going to be doing all of it to the y value. Okay, and remember again, our textbook doesn't require you to find these. Oh, gosh, sorry guys, I'm picking up everything wrong. There we go. So you could cross that off. It's not going to be something that we need to find in our class. Okay, so let's go ahead and use these, and then we'll talk about that a squared minus b squared equals c squared. It's like, why is that the case? Okay. All right, so we have to graph this. So a squared is going to be the bigger number. So a squared is going to be 16, which means that b squared is going to be 9. So if we square root, we get that a equals 4 and b equals 3. So this is under x, and this one was underneath y. Okay. Now the center is a little bit more challenging this time because it's not just 0, 0. But remember, when we pull these things out of the parentheses, we got to change their signs. So it's going to be -2. All right, so I'm going to go to -2, +3. That's going to be the center this time. Now we know that we're going 4 in the x direction, but it's going to be from that center. So I'm going to go 1, 2, 3, 4 to the right. 1, 2, 3, 4 to the left. And then the 3 would be in the y direction. So 1, 2, 3 up, and 1, 2, 3 down. We're ready to draw our ellipse. Very, very similar. It's just not centered at 0, 0 anymore. Okay. So you can get the vertices from the picture. Let's do it both ways, okay? Technically, if I'm using those formulas, because I'm bigger in the x direction, I'm going to take my center and I'm going to add and subtract a to the x value because I'm bigger in the x direction. And remember, it's a because a is always the letter that goes with the vertices. B is the letter that goes with the covertices, and C is the letter that goes with the foci. So for example, if I'm asked to find the foci, which I am, well, then I would be adding and subtracting C to the x value, but it'd be C, right? Okay. All right. So let's go ahead and do the math here. -2 plus 4, comma 3, right? Would be, let me move this out of the way, actually. -2 plus 4 would just be 2. And then -2 minus 4, comma 3. That one would be -6, comma 3. Let's go check and see if these are right, because these are what we got for our vertices. Let's go check. So 2, comma 3. 1, 2, 1, 2, 3. That looks great. And then -6, let's see, 1, 2, 3, 4, 5, 6. Yes. Okay. Good. Now, of course, if you just drew a good graph, I'd just get it from the graph. I would not have to deal with all this formula stuff. But sometimes they don't make you graph it. So if you can do it without a graph, cool. Save yourself some time. All right, so now let's go into the foci. Now, in order to do the foci, you got to do that a squared minus b squared equals c squared. So a squared is 16, b squared is 9. 16 minus 9 is 7. And then we'll square root, get c equals square root 7. But we'll see, we don't need the plus or minus on it. I mean, it is a distance, but we're going to plus or minus it in the formula just because we're going to go to the right and to the left. Okay, and by the way, that's got to be what, 2 point something? 7? 2.6? All right, so 2.6-ish. So where these would be located is we would go 1, 2.6, bam, and 1, 2.6. So notice they're along the major axis, as they should be, and they're not as far out towards the vertices as the last couple we've graphed. And that makes sense because this ellipse isn't as flat, you know, it isn't as skinny as the other ones. This one's starting to become more circular than the last two, which means our foci should be creeping more towards the center. So remember, the closer they get to the center, the closer they become more like a circle, because instead of being two, they merge into one, right? Which is exactly how a circle is. It's only got one spot where you would put the pen and with the string, okay? All right, so to find those, or to write those, how we're gonna write them in my math lab, we're gonna take the center, -2, 3, and we are going to add and subtract √7 to the x value because we went in the x direction. All right. You know what? I'm just going to box the whole thing. So let me delete this box out if I can. All right. Okay. Hopefully this is starting to make a little sense. Let's see when I want to put in. This. Okay. Now, this is going to be really close to what we did with circles, but slightly different. Okay. We do start off by grouping together the x's. And then grouping together the y's. And even moving the constant over to the other side like we did. So far, this is exactly like what we did with circles. Now, one difference, though, is I cannot complete the square when there's a leading coefficient. So I have to factor the 9 out of both of these terms. And I'm going to leave a little space. And for this one, I have to factor the 5 out of both terms. Okay, so that was different. That was new, this whole factoring out the leading coefficient. Now we're going to go ahead and complete the square with the 2 for starters. Remember, the formula is to take half of b and square it. So we're going to take half of 2 and square it. Well, half of 2 is 1, and 1 times 1 is 1. So we're going to put a +1. Now, that's not really a 1 that I added into the problem. Okay, don't do this, you guys. I'm going to erase it in a second, but I just want you to see why it's not a 1 that we added. If we distribute, we get our 9x squared, which matches with that. We get our 18x, which matches with that. We have a 9, which is like nowhere in the original problem. We have a 5y squared that matches with that. We have a -30y that matches with that. And then we have our -9. So notice there's this extra 9 that was nowhere to be found in the original problem, right? Extra 9. So if that means I added a 9 into the left-hand side of the equation, so I have to add a 9 to the right-hand side of the equation. So just to kind of recap, or kind of give you a shortcut for how to do that, it's not 1 that you'll be adding to both sides. What you're going to do is you're going to distribute the 9 to the number and say that's a +9. Then I need to put a +9 over here. All right, let's do it again. But this time we're going to do it for the b on the y value. So -6. So we're going to take half of -6 and we're going to square it. So -3 times -3, this would be a 9. But it's not really going to be a 9, right? When I distribute the 5 to the 9, I get 45. So we really added a 45 into the problem. So that's the trickiest part. If I could say where my students mess up, it's right there, because they'll put a +1 and on both sides of the equation, the +9. You've got to remember to multiply it by that front number. Okay, so we have 9 times something squared and 5 times something squared. And these 9s are just going to cancel each other out. So it looks like we get 45. Now, remember we said there's a shortcut. Don't work too hard. That whatever was inside the parentheses before you squared, that's going to be how it factors. So I'm going to drop a +1 in right there. And that makes sense. 1 times 1 is 1. That gets me the back number. But 1 plus 1 is 2. That gets me the middle number. We did the same thing with the -3, and we dropped that in here. So this is going to say, oops, I meant to do that with green. So this one's going to say y minus 3. That makes sense. What's -3 times -3? +9. And -3 plus -3 is -6. And we're almost there. Just don't forget the right-hand side always has to equal 1. So we're going to divide by 45 to everybody. And that's how we're going to get that equals 1. Perfect. All right, now 45, 9 goes into 9 once. 9 goes into 45 5 times. 5 goes into 5 once. 5 goes into 45 9 times. So it looks like we have x plus 1 squared. Oops, I should write this a little higher. X plus 1 squared over 5 plus y minus 3 squared over 9. That's going to be our equation. Okay, so let's go through the things that we need to find. Okay, so a squared is always the bigger number. So a squared would be 9 in this case, and b squared would be 5. So if we square root, we get that a equals 3. And if we square root here, well, it's not going to be perfectly square rootable, huh? So it just stays square root of 5. All right. Our center, take a moment, see if you can get it. Hopefully you said -1, +3. So we're going to go to -1, +3 to start this ellipse. All right, now the 3, that was the a was underneath the y this time, right? So this was under y, and this one is under x. So I'm going to go 3 in the y direction. So in other words, up and down. So 3 up, 1, 2, 3. 3 down, 1, 2, 3. And square root of 5, well, it's going to be 2 point something. Square root of 5. 2.2-ish. Okay, so I'm going to go 2.2-ish. And 1, 2.2-ish. And that's going to be my, oops, wrong. All right. So since it's bigger in the y direction, right? It's bigger in the y direction. That means that when I find the vertices and the foci, that I am going to be, let me move this. I'm going to be doing it to the y value. Same thing for the foci. I'm going to be doing it to the y value. Now remember, for vertices, it's the letter A. So the A is 3. For foci, it's the letter C, which we haven't even found yet. Okay. So let's go ahead and get these vertices really quickly, though. 3 plus 3 would be 6. And 3 minus 3 would be 0. So apparently, they're going to be at -1, 6. Perfect. That is exactly correct in the picture. And -1, 0. Spectacular. Again, don't use the formulas if you've got a graph. You know, I'm just practicing it in case there's questions where we don't have the graph. Now for the foci, we're going to need C. So let's bust out good old a squared minus b squared equals c squared. A squared was 9. B squared was 5. Holy moly, we got our first really nice number to square root. So it looks like C is going to be 2 for this. So we would add and subtract 2. So let's see here. 3 plus 2 is 5. 3 minus 2 is 1. Now, so for our foci, we would go 2 up and 2 down on the major axis. So let's see if we're right. Negative 1, 5. Let's see here. Negative 1, 1, 2, 3, 4, 5. Perfect. And the other one is at negative 1, 1. It's perfect, you guys. All right. I'm going to go in the box. We need center. We need the vertices. Okay, let's just take a minute to talk about that Foci formula. Why is it a squared minus b squared equals c squared, right? Deriving the Foci formula. Now, when we watched that video, in the video, what he noted was that the string was the length of the major axis. He said it a few times. He even pulled the string off. Okay. Let me get a couple things in here really fast that we're going to need. Okay. So I'll erase this in a second, but he had these pins, right? And he had this string, right? And he said that the string was the length of the major axis, and he pulled it off, and it was exactly this long when he pulled it off, okay? So I'll just put an X. I always put X's for my foci, you guys. Okay. So if I put the string right here so that it was pulled like this, perfectly at the top. Okay. So the string, let's talk about how long the string is. So if we have an ellipse, we know that the distance from the center out to a vertex is the letter A. And same thing over here. The distance from the center out to a vertex is the letter A. So that means that the whole thing must be A plus A. So the whole thing must be 2A long. Okay, so our string is 2A long. I'm going to erase that terrible picture because it's not drawn very well. Oops. But I am going to write down what we found out from it, right? Which is that the string is 2A long. Okay. So if I place it, you know, not someplace like this, where it's not divvied up perfectly, but I placed it exactly how we placed it here, well, then that must mean that this must be A and this must be A. That way the string will add up to A plus A, in other words, 2A. Now we know that letters-wise, from the center to a co-vertex or the minor axis endpoints, that's the letter B. And we know from the center to a focus is the letter C. So on our right triangle, it's not set up how we're used to having our right triangle be set up. We're used to C being the hypotenuse, right? So if we take this right triangle where we have B here, C here, and A here, and we do the Pythagorean theorem to it, right? Then the Pythagorean theorem in this case would be B squared plus C squared equals A squared, or if we subtract the B squared from both sides, right? Then we end up with C squared equals A squared minus B squared. Okay, and there's our formula. So the reason why it's not what we're used to is because the positions of A, B, and C are not where they usually are. So having a deep understanding of that string being the length of the major axis, in other words, A plus A long, so 2A long, was a big deal for this. Okay, so I like these ones. These ones are like puzzles. You know, our goal is to write the equation of the ellipse, and they'll give you certain things. So let's see what they've given us here. They've given us that the center is going to be at 1, 3. A focus is going to be at negative 2, 3. So let me try to draw this stuff. So at 1, 3, let's say this is 1, and we'll say this is 3. That's where the center is. Then a focus is at negative 2, 3. I always draw an X for the focus so I know the difference between it and the other things. And a vertex is at 5, 3. Okay. All right. So this is kind of funky looking, but they gave us everything we needed to know. They gave us the distance from the center to a vertex. That's the letter A. So if we wanted to find out how long that is, well, that would be the distance between 1 and 5. So A would be 4 long. Then they also gave us the distance from the center to a focus, which is the letter C. Well, that would be however far -2 is from 1. Well, that would have to be 3, right? 2 spaces to get to here and 1 more. So that adds up to 3. So they gave us everything we needed to get this done. Let me just go ahead and draw what the ellipse would look like loosely. Okay. So the ellipse would look something like this. Boy, I didn't do a good job there. There we go. They didn't give us the other focus, right? And the other vertex, but that's what our ellipse would look like. Okay. All right, so let's kind of roll with what we have and see if we can figure out. So my first question for you is going to be, which one of these equations is the one that we want to use? Assume that maybe you have these written down on like a note card and you're on your test and you're, man, which one of these do I pick? You want to make sure that you would be able to pick the right one. The only difference between the two is the a squared and the b squared switch spots, right? So you have to sit there and think which one of these we would want. Now our ellipse is bigger in the x direction. It's not bigger in the y direction. So that means that we would want this one because the a squared, which is the bigger number, is underneath x. So we will not be using this one for this problem. So let's substitute in what we know, okay? We know the h and the k. They straight up gave us the center. It's 1, 3. So remember, change the signs when you put it back in. If it's a positive one, here it's going to be a -1. And then if it's a +3, here it's going to be a -3. Okay. All right. A squared. Well, they gave us A. A is 4, right? So if A is 4, then A squared would be 16. So we'll put the 16 here. Now, the only problem is we're missing B. Then B squared, right? And that's what we need to finish this off. So that's when we're going to bring back that Foci formula. A squared minus B squared equals C squared. A squared is 16. B squared, oh, I better square it, huh? If C is 3, then C squared must be 9. Okay. So we'll go ahead and subtract 16 from both sides. So we end up with -b squared equals -7. We'll divide by a -1. B squared equals 7. Now here you got to resist the temptation to square root both sides. I mean, we've done that so many times in our lives that I see why we would do it. But what we need is b squared. So we actually want to leave it squared, you guys. Gosh, there were so many times I squared root that and I didn't need to. Okay. And so that's going to be the equation. So this is what I mean by you've got to know what A is, what B is, and what C is. If you have that down solid, then something like this isn't going to get you. They gave us the center and they gave us a vertex. Well, they just gave us A. They gave us the center and they gave us a focus. Okay, well, then they gave us C. Okay, so you've got to make sure you understand what A, B, and C stand for to be successful. Okay, an art museum is adding a new exhibit room in the shape of an ellipse. The director wants to mark the foci so that a tour guide can stand at one focus and without speaking loudly can be clearly heard by a group touring the museum. If the room is 64 feet long and each focus is 5 feet from the outside wall along the major axis, how high is the ceiling round to the nearest tenth of a foot? I've actually been in a whispering room and it was really, really cool. Hopefully you get a chance to go and visit. If you just Google whispering rooms, there's a lot of famous ones. So maybe you find yourself traveling and maybe you could go visit one and just experience it. Okay, so let's see here. Our room is 64 feet long, and each focus is 5 feet from the outside wall. Okay, so I'm just going to draw an ellipse that's 64 long. Oops, sorry, you guys. Draw an ellipse that's 64 long. So let's make that 60. So from here, maybe I don't want to do it in red. So I'm just going to say from here all the way to here, that's going to be 64 feet. Now I actually don't want the 64. I want half of 64 because I want from the center all the way out to a vertex. So half of 64 would be 32. I'm going to pop quiz you. Which letter did we just get? If you said A, then you are correct. Okay. Now it says each focus is 5 feet from the outside wall. Well, that's not how it was usually given to us. They're not giving us this distance, which is what we want. They're saying it's 5 feet from the outside wall. So in other words, that's what's going to be 5 feet. Okay. Well, I don't want that. I want the distance from the focus to the center. Okay. So how we're going to get that is we already know this whole thing is 32, right? So if I do 32 take away 5, then that must mean that it must be 27 from the focus to the center. That way we have 27 plus 5 more. Bam, there's our 32. Okay, another pop quiz. What letter did we just find? Hopefully you said C. Okay, so we're going to go ahead and try to write the equation here. Let's see, what do we need to find? How high is the ceiling? Okay, all right, so we want to find out, this color, I guess. We want to find out how long that is. Okay, so in other words, we want to find out what B is. Then we'll know how high our ceiling is. Okay. All right. So let's see here. A squared minus B squared equals C squared. Seems like it would be important here, right? Okay. And that's because that distance I just drew is the letter B. Okay, so we have A, we just haven't squared it yet. So we got to do 32 times 32, you guys. So I'm just going to go to my calculator. 32 squared, 1,024. So 1,024. And then we got to do 27 squared. We got to try to get C squared. So let's do 27 times 27. Oops. 729. Okay, so let's go plug it in. So A squared, we said, was 1,024. So we're going to subtract 1,024 from both sides. $729 take away 1,024. -295. And you get squared equals 95. Square root both sides. So we get that equals whatever the square root of 295 is, right? Round to the nearest tenth, it says. So let's see, square root 2, oops. $17.2 then, because the 7 is going to round the 1 up. So 17.2. And this is going to be feet. Everything's in feet, I'm hoping. I didn't even read that. Yeah, everything's in. So at this point, you might be wondering, like, okay, so we found B, what does that mean? And honestly, the problem's not really well written to kind of decide if that's enough. Because from what I've seen when I've been looking up whispering rooms, is they could be designed a lot of different ways. I'm just gonna go show you some of the ones that I saw when I was like on the internet. So if our whispering room looks like this, then we're done. I'm gonna call this the snow globe one, right? Then we're done. The answer is what it is, okay? Because basically you're saying this is the ground, right? Oops, this is the ground right here. So you have the ground and the ellipse part of it, you're only taking half of it. And so when we found B, we've actually found the height of the ceiling, okay? So maybe this is the answer. If the whispering room was designed in the following way, where it's like, okay, here's normal, kind of a normal room, but then they decide to add the half of the ellipse onto that, then the B would be here. Boy, this is the worst drawing ever, but hopefully you get the idea. Well, then the height of the ceiling would be B plus whatever this height is. And I've seen lots of whispering rooms that way. In fact, most of the ones that I Googled looks like that when I first went on here. Like you can see this one over here. The whole thing is an ellipse. They kind of start the ellipse at a certain height. Here's a drawing of it. So this is that same type of a deal where you've got your regular room and just the top half is the ellipse, which that's actually, I think, the one that's going to get you that best whispering room sound, because if you put the foci through where most people's heads are, right, then you're going to get that whisper effect better. And so I'm kind of having an issue with how this word problem was written, but you know what? We have the B. So let's say that we do know that distance there, we could always just add it to the B. When I looked in the textbook, they had 17.2. So we're done. But I mean, some questions linger for me as to how this whispering room is designed. But we'll move right along, okay? All right. So there's a reflective property of ellipses where whenever a ray leaves one focus and it bounces off the ellipse, it will always reflect back and pass through the other focus. So you could kind of see that in those pictures I actually just pulled up. But let's say that we do have an ellipse, and let's get ourselves a major axis. And we'll have some pretend foci. Pretend this is our foci. I'll put them close to the edge because this one's not very circular. So if a ray leaves one of the foci, it's always going to reflect off and hit the other focus, okay? That's the property, reflective property of ellipses. So in the medical field, I don't know how to say this, so if I'm not saying lithotripter, that's what I would guess, but they actually use ellipses to help kidney stones get passed. So let's just kind of read this so you can see. It says, an elliptical water tank has a major axis length of 6 feet and a minor axis length of 4 feet. The source of high energy shock waves from a lithotripter is placed at one focus of the tank. To pulverize the kidney stone of the patient, how far should the stone be positioned from the source? So you're pretending that this is like a big water tank and you've got this lithotripter, right? It's going to send a shock wave out. It's going to bounce off the edge of the tank. And right here is where we need to place the kidney stone. Okay. So let me just go ahead and write a few things in here. I don't know why they don't always do this. Maybe it's just expensive. A lot of times they're just like, good luck, pass that thing, you know? I don't know if it has to be a certain size. And then they're like, okay, we'll go ahead and do this. I'm not sure the details on it. Anyhow, all right. So we know that the major axis length is 6. So in other words, we know that, again, this whole thing is going to be 6 long, right? But we don't really care about the whole thing. we care about from the center out to a vertex. That's going to be 3 then. It's 3 plus 3 is 6, and that's going to be the letter A. Hopefully you'll guess an A. All right, and then the minor axis length is 4. So from the top all the way to the bottom, we know that's 4. But again, we don't want all the way from the top to the bottom. We want from the center up to the ellipse. That's going to be 2, and that's going to be the letter B. So we have A and B. Okay, so what they want us to find, though, if you think about it, is we really need to find, because it says how far should the stone be positioned from the source? Well, this is the source. This is the source of the shock waves, right? Well, if I could find C, the letter C, right? If I could find this distance right here and add it to itself again, right, 2C, then I would know how far this patient needs to stand from the source. So our goal is to find C. So I think this will just be a simple application of the A squared minus B squared equals C squared. So A squared, so let's see here. We know A is 3, right? So if A is 3, then A squared is going to be 9. We know that B is 2, so B squared is going to be 4. So we end up with 5 equals C squared. We'll go ahead and square root. So we get that C is the square root of 5. So if we have square root of 5 for this, and then square root of 5 for this, the square root of 5 plus the square root of 5, we just add the numbers in front. We're going to add these ones. So we're going to end up getting 2 square root of 5 feet for where or how far from the source that the patient should be placed. All right, kind of cool, right? Sometimes doing these math word problems is fun because I get to learn about a bunch of other things that exist. And these were really 2 cool problems here. All right, I believe that's it. That is. All right, you guys, thank you so much for joining me. Hopefully this helps you out with your homework. Take care.